Welcome. The topic we'll be discussing in this lecture is implementation of page table at hardware level. In the hardware level, how the page table uh, is get implemented. That's what we are going to discuss here. So basically, there are different ways of implementing the page table. I mean, different methods may slightly vary with each other. So we will discuss some of the commonly used methods. Okay. The first method and the most simplest method to implement the page table is to use the CPU registers. Use the dedicated registers which is available with the CPU to implement the page table. That is, here the page table will be nothing but the entries in the register, right? So basically, what is a page table? A page table is a table which translates the logical address to physical address, right? So each entry in a page table will correspond to some physical address, okay, and it will be indexed with the appropriate logical address, okay. Maybe logical address 0 may refer to physical address, the page number. It's not exactly the it does not index to the address exactly. It actually index to the page number. For example, the sorry for example, the page number in the logical address, it may be 0. This may in the page table, this may refer to 5. That means it is referring to the fifth frame of the main memory, okay. Similarly, uh, 1 in the logical address, the page number may be 1, but that may refer to 10 in the 10th frame in the actual physical memory, right? So for every entries, we may use the registers. So the first and the most simplest method to implement the page table is to use the dedicated registers. Okay. But this method is okay as long as the size of the page table is small. That is, if the page table contains up to 256 entries, this method is okay because we don't have many registers, right? We have very less number of registers, and the size of the registers also we should take it into account. So this method will be fine if it is if the size of the page table is up to 256 entries. But today's page table, it has many entries. It may go up to 1 million entries. So we cannot use registers. We cannot depend on the CPU registers for page table, right? So the second method, the next method, what it suggests in the sense, it is to use something called as PTBR. PTBR represents page table base register. Page table base register. In this case, what happens in the sense, there will be some register in the CPU. Only one register will be using in the CPU, and that register will be called as PTBR. That is page table base register. So this will refer to the starting address of the page table. This will refer to the starting address of the page table. And actually the page table will be in the main memory. The page table will reside in the main memory, okay. And whatever the starting address of the page table, say say this is the page table for process 1. This is the page table for process 1. Say its starting address is 2000. Okay. So currently if process 1 is executing, then 2000 will be stored here. Then 2000 will be stored here. It means that the page table is starting at location 2000. Okay. So with this, the CPU knows that where is the page table located. Okay. So this is the page table for process P1, but maybe there may be some other process P2. For that, the page table may be different. So currently P1 is executing, so PTBR is loaded with 2000. If there is another process P2, it will have its own page table. Another process P2 will have its own page table, okay, and it will have its own set of entries. right? And maybe this page table may start at location 7000. So at this point of time, CPU is executing process 1, but later it may context switch to process 2. If it is context switch to process 2, then this PTBR will be changed to 7000. Okay, right? So with this, the CPU will understand where is the page table available in the main memory. And then CPU will use the logical address. The logical address will contain the page number and the offset. Okay, the logical address will have the page number and the offset, which is D, which we normally represent as D. Then this page number will act as an index to the page table, which will give the appropriate physical address, appropriate page number, appropriate frame number, and that will be what you call, that will be multiplied with the frame size, and then it will be added with the offset. Like that, we'll fetch the physical address as usual. Okay. So the second method, what it suggests in the sense, it suggests to use an additional register called as PTBR. This PTBR will be a CPU register, and this register will point to the starting address of the page table. Okay. Along with that, it also uses another register which is called as page table length register, which indicates the size of the page table. So the second method, it uses two registers. One is PTB or page table base register, and the other one is page table length register. Page table base register will hold the starting address of the page table, and page table length register will hold the size of the page table. Okay, and through that the hardware this will understand where the page table is located in the memory. Okay. But there is a drawback with this mechanism. The drawback with this mechanism is it requires two memory access. Whenever you want to fetch a address, it requires two memory access. First is you should access the page table based on the value that is stored in the PTB, or first you should access the page table. Then you should, then from the page table, the CPU should take the logical address, and then it should identify the corresponding physical address, and then it should add the offset, and then it should refer the actual memory. So there are two memory accesses. One is to access the page table, and the next is to access the memory. Okay. So actually this two-way access will create a lot of delay, and we cannot accept delay. We cannot accept delay because CPU's time is very precious. So delay is intolerable. Okay. So so because of this reason, we are going for the next type of page table, which uses a technique called as TLB, translation look aside buffer, which uses a technique called as translation look aside buffer. This is a very small buffer, and at the same time, it is a high speed memory. It is a high speed memory, and it will be located in cache. It will be located in cache. It is also called as associative memory. Okay. So the drawback with PTB or page table based register technique is it requires two memory access. First, the CPU should refer the page table base register and identify the starting address of the page table, and then it should and then the CPU's logical address should be converted to the physical address. So there are two memory accesses by which creates time delay, and this kind of delay is not tolerable in case of considering the considering the what you call the considering the CPU resource utilization, right? So we are going for next technique, which suggests to use something called as translation look aside buffer, TLB. Okay, TLB stands for translation look aside buffer, and these are this is a special small fast lookup hardware. This is a special, small, and fast lookup hardware cache. Okay, it's a cache memory. So it will be a part of the cache memory, right? Okay. So let us understand how TLB works. Okay, let us understand how TLB works. Okay, so before this, I'll show you how TLB works. So basically TLB is a will be located in cache memory. Okay, it itself is the cache memory. That is, it's a high speed memory and it is small. So TLB is basically a table. TLB is basically a table which contains two columns. The first column refers to the page number and the second column refers to the frame. Okay, so it just maps every page to a particular frame number. Okay, page 0 refers to frame 5, page 1 refers to frame 10. Okay, page 2 refers to frame 7. Like that, it just maps every page to a particular frame. Okay, so basically each entry in a TLB, translation look aside buffer, consists of two parts. You can say one is a key, the other one is a value. The key is the page number and the value is the appropriate frame number. Okay, and what happens in the sense, as we know, CPU creates the logical address. So the logical address consists of what? Page number and the offset. So the logical address consists of page number and the offset. Okay, so the logical address that is created by the CPU will have the page number and offset. That page number will be checked with all the entries in the TLB, in the translation look aside buffer. So this is translation look aside buffer. So it will check for which page number what is the frame number. Like that it will check. If a match is found, and this checking will be done fastly. Okay, it won't take much time because this memory itself is a cache memory. Okay, so it will check whether a match is being found for a particular page number or not. If a match is found, then the appropriate frame number will be taken. Then the appropriate frame number will be taken, and whatever you want to do. So normally we multiply the frame number with the page size, and then you add it with the offset. Okay, then add it with the offset, and as a result, what you get is the physical address. Okay, then you access the physical location. So this is how translation look aside buffer works. Okay, but one thing we should understand, as we have already discussed, translation look aside buffer is a small memory. Okay, it is a special small fast lookup hardware cache. Okay, so it may not have mapping for all page numbers. It may not have mappings for all page numbers. Some page number will be mapped, some page number will not be mapped. Okay, so first the CPU will should check whether there is a mapping is available for this page number or not. Okay, if the mapping is available, it is fine. If the mapping is not available, then that is called as TLB miss. Okay, if the mapping is available, that is called as TLB hit. Okay, if the mapping is available, then you got the frame number. Then from the frame number and offset, you can identify the physical address. If mapping is not available, then that is called as TLB miss. If TLB is missed, okay, if the particular page number cannot be mapped to a frame number using the TLB, then again the CPU will refer the page table. Okay, now the CPU will go back and refer the page table. Okay, so you should understand one thing very clearly: page table will be located in the main memory, right? Whereas TLB is a cache. Whereas TLB is a cache, so TLB is a high speed memory. Okay, so now as this particular page number is not the particular page to frame mapping is not available in the TLB, the hardware checks the page table. So this is the page table which is stored in the main memory. Okay, so obviously in page table the respective frame number will be available. Okay, so now you identify for this particular page number what is the frame number. Identify the frame number, and then that identified frame number, along with that offset, you can identify the physical address. Okay, not only that, once you identified that particular page number, once you identified that this particular page number maps to this frame number, then that should be added to the TLB. Okay, because next time if the CPU wants to access the same page, then it can get it from TLB. because getting from TLB is faster. Again, if it is not in the TLB, once again going and fetching from page table, all these things are time consuming process. So once if it is found in the, once if there is a TLB miss, and then if it is found in the page table, then you should be converted to physical address. At the same time, that mapping also should be added into the TLB. Okay, that mapping should be added into the TLB. Say for example, this page refers to page 3, and that corresponding frame number is frame 18. So it means page 3 is mapping to frame 18. Like that, it should be added into the TLB. Okay. Say assume that there is no space in the TLB. TLB is already full. Then how will you add? If TLB is already filled, then some location in the TLB should be replaced. Then some location in the TLB should be replaced. For replacing, you can follow any one of the techniques. Like you can follow either LRU, least replacement technique. Okay, so either you can use LRU, which means least recently used. Yeah, LRU stands for least recently used. So out of all the page number, which page number was least recently used? Okay, that is which is used long back. That page you identify, and that you replace with the new page number and the respective frame number that was fetched from the page table due to the recent TLB miss. Okay, so LRU is one technique. Otherwise, you can use round robin technique. Okay, round robin technique. Okay, that is you follow some order in which order it should be replaced, and if currently this page is replaced, then the next page should be replaced, like that round robin technique. Or you can follow a random technique, just randomly replace any page number, uh, replace any, remove one particular page, and in that place you add that new page number and the frame number. Okay, so I think this is clear. So this is how overall the concept of TLB works. So basically TLB maintains a table, and that table is called as translation look aside buffer, and it is a small fast cache memory, and it basically it maps it, uh, it consists of two parts, a key and a value pair. A key refers to the page number, and the value refers to the frame number. And the CPU's logical address consists of two parts, the page number and offset. So the page number will be checked whether it is available in the TLB or not. If it is available, the respective frame number will be taken, and along with the offset, the physical address will be created. If it is not available in the TLB, then we call it as TLB miss. Now the CPU will get back to the page table which is in the main memory, and from there it will get the frame number, and with the frame number and the offset, it will create the physical address. Apart from that, the newly identified page number and the frame number should be added into the TLB if there is sufficient space. If there is no sufficient space, then one entry of the TLB should be replaced with the new page number and the frame number. So to replace, we have to identify which should be replaced. For that, we can use techniques like LRU, least recently used entry, or round robin, or we can randomly update an entry. Okay, so this is how the TLB works. Okay, so this diagram shows clearly exactly how TLB works. So this is TLB. Okay, so this part is TLB, and this is as we already discussed, this is a what do you call it? This is a special small fast lookup hardware cache. Okay, so it's a cache memory. It can consist of two columns. It consists of two columns, which is basically, you can call it as a key and a value pair. The key is the page number, and the value is the frame number. Right. The CPU creates the logical address, which consists of the page number and the offset. So the page number will be mapped with the TLB. If it is available, then you get the particular frame number. Then the frame number can be combined with the offset, with some operation, and with that you can fetch the physical address. Suppose if the page number is not available in the TLB, because TLB is of limited size, it is not that TLB will have the page number to frame number mapping for all the pages. No, it may not have for all the pages. So if a particular page is not available in the TLB, then it means that TLB miss. So if there is a TLB miss, we refer to the page table and then identify for that particular page number what is the frame number, and then fetch the frame number, and then along with the offset identify the physical address. So if it is a TLB hit, we take this path. If it is a TLB miss, we take this path. Okay. If there is a TLB miss, then the new page number and the frame number should be added to the TLB if there are sufficient space. If there is no sufficient space, then any one of the TLB entries should be replaced either by following techniques like LRU, round robin, or random replacement technique. Okay, so this is the whole overview of implementing a paging hardware with TLB. Okay, fine. Now coming to the next part, some of the TLBs also include something called as ASID, address space identifier. Some of the TLBs also includes something called as ASID, address space identifier. Okay, so what is this address space identifier? Let us see. See this particular diagram, you can see here. This particular diagram actually, as we already discussed, there will be a different page table there will be a different page table for different what do you call, there will be a different page table for different process. Okay, for every page table there will be a different for every process there will be a different page table. Okay, for every process there will be a different page table. So this, with this diagram, what does it mean? In the sense, this particular page table corresponds to one particular process alone, maybe some process pi. Okay, some process pi. Then it means that this TLB also corresponds to only this process, that's all. Okay, this TLB also corresponds to this process. Say, so CPU will execute this process for some times. Maybe after some time, say CPU want to execute some other process PJ. Then what will happen? Everything you should change. This TLB should be totally flushed. It should be removed, and the TLB corresponding to PJ should be loaded. And the TLB corresponding to PJ should be loaded. Okay. So that means every time when a new process comes in, the new TLB should come. Are you getting? Every time when a new process comes in, the new TLB should come. Okay. So to avoid that, we can use this technique which is called as ASID. To avoid that, with ASID, what you can have in the sense, with ASID, multiple page tables can be, multiple process can be referred using the same TLB. Multiple process can be referred, or multiple process page number can be mapped to a frame number using a single TLB by using something called as ASID, address space identifier. Okay, so as a whole, how it works in the sense, let me tell you in a simple way. So in this TLB, one more column will be added. Okay, so normally TLB contains only two columns. What are they? They are the page number and the frame number. That is a key value pair. But with ASID, address space identifier, the TLB will have one more column, and this column will be called as ASID. This column will be called as ASID, and this column will say whether this particular page number and the frame number, whether this particular page number corresponds to which process. Okay, so whether it is corresponds to process 1 or process 2. Let us assume for a simplicity's sake there are two processes. Currently there are two processes, say P1 and P2. Say this is the page table for the process P1. Okay, this is the page table for the process P1. Okay, say this is the page table for the process P2. Okay, So the page numbers are generally same, right? Page numbers are generally same. So the page numbers of the P1 process will be what? It will be 0, 1, 2, up to maybe some n or n minus 1. Okay. It will map to some, each of this page number will map to some frame number. So this may map to 7, this may map to 8, this may map to 6, like that it goes on. Similarly for P2 also, the page numbers will be 1, 2, 0, 1, 2 up to n minus 1. Okay, but the frame numbers will be different. If the page number 0 of process 1 is referring to the frame 7, then page 0 of process 2 surely will not refer to frame 7. It may refer to frame say 9. So whatever the frame which is coming here in process 1, it will not appear for process 2, because frame refers to the physical memory. Okay, I think you are getting, because frame refers to the physical memory. So this two will not match. So this will refer to frame 7 means seventh frame of physical memory. It is for page 0. It is for page 0 of process 1. It is for page 0 of process 1. Okay, similarly this is ninth. Page 0 of process 2 is referring to ninth page, ninth frame. So it means that this ninth frame is for page 0 of process 2. Is for page 0 of process 2. Okay. So this ASID, address space identifier, what it does in this sense, it adds one more field to the TLB, and this field, it just identifies the process number, which process it is, whether this particular page number belongs to process 1 or process 2. It is, say it is process 1, the next page it belongs to process 2, like that it will include the identification, some identification of the process. Say next is also process 2, next is process 1, like that it will include an identifier for the respective process. It will include an identifier for the respective process. Okay, so now if CPU creates a logical address, say CPU is creating a logical address for, say assume that this logical address is for process P1, is for process P1. Say the logical address it is creating is for the process P1, it is creating a logical address, say it is 7 and some offset value D. Okay, then it will check whether the page number 7 is available here or not. First it will check, okay, 7 is available somewhere. Then again it will confirm what is the process number, whether it is process 1 or process 2. 7 is there, but if it is for process 2, then it won't take that. If 7 should, there should be two match, there should be a, the process I mean the page number should be matched, and also the process number also should be matched. Okay, then it will fetch this particular frame number, and with that frame number and offset it will calculate the physical address. Okay, suppose 7 is there, but this 7 belongs to page 2, process 2. 7 is there, the page number 7 is there, but it belongs to process 2 means then actually it will lead to TLB miss, and and it will check the appropriate what do you call, for page number 7, what is the appropriate frame number, it will identify from here, and then with that frame number the physical address will be created, and that frame also will be added to TLB along with the process number. Okay, so this concept is called as ASID. So with ASID, what is the benefit in the sense, uh, it could with the ASID we can have multiple processes can be accessed by using a single TLB. Otherwise, whenever the CPU context switched, the entire TLB should be flushed out, and it should be newly updated for the new process. Okay, so this is about ASID, right? Address space identifier. Okay, okay, fine. Then we'll discuss some small example here. So if the page number is available in the TLB, then that is called as TLB hit. If it is not available in the TLB, then that is called as TLB miss. Okay. The hit ratio, of TLB is nothing but the percentage of times that a page number is found in the associative register. Associative register is nothing but the each entry of the TLB is called as associative register. Okay, each entry of the TLB is called as associative registers. So hit ratio is what the percentage of time that a page number is found in the associative register. Okay, let us assume that for a particular process, the hit ratio is 80 percentage. That is 80 percentage of the time the page number is available in the TLB, and remaining 20 percentage of the time it is not available. Okay, if it is available in the TLB, then to access the memory, say we need 100 nanoseconds. That is already you have the page number and the frame number, then just convert it to physical address and directly access. So you need only 100 nanoseconds if it is a hit. If it is a miss, let us say we need 200 nanoseconds. The CPU requires 200 nanoseconds if it is a miss. Because if it is a miss, it has to go back to the page table, then it should identify the frame number, and then it should access. So there are, for accessing the main memory, it may take more time. So for hit, let us assume it takes 100 nanoseconds, and for miss, it takes 200 nanoseconds, because again it has to go back to the main memory and access, right? So, mm, mm, so go back to the main memory and refer the page table, and then it should access. For that, 200 nanoseconds. Okay. So here hit ratio is 80 percentage. So 80 percentage, if you convert it to fraction, so 0.80 into 100 nanoseconds. Okay, if it is a hit, because if it is a hit, it needs 100 nanoseconds. 80% of the time it is a hit. Remaining 20% of the time it is a miss. So plus 0.20 into 200 nanoseconds. Okay, so the effective access time is 120 nanoseconds. Okay, the effective access time is 120 nanoseconds. So here, so in this case, we suffer a slowdown of 20 percentage. We suffer a slowdown of 20 percentage. How we say we suffer a slowdown of 20 percentage? Because if it is 100 percentage, say alpha is 100 percentage, say hit ratio is 100 percentage. Okay, then what will be this? This will be zero point 0.1 into 100. Okay, if alpha is 100 percentage, then this will be 0.1 into 100. Okay, and this will be 0 because there is no miss at all. So 0.1 into sorry, not 0.1, 1 into 100. Okay, not 1 into 100. 1 into 100 will be 100 nanoseconds. Okay, so that is an ideal case. That is an ideal case that may not be possible. Okay, but compared to the ideal case, our result is how much time it is. It is more. It is 120 minus 100 is 20. So 20 percentage it is slowed down. Okay. Let us see another example. If the hit ratio is 99 percentage, and let us consider the same memory access time. If it is hit, the memory access time is 100 nanoseconds. If it is miss, the memory access time is 200 nanoseconds. Then it will be, then the effective access time will be 0.99 into 100 plus 0.01, because only 1 percentage there is a miss into 200, which is 101 nanoseconds. So in the second case, the second case, the slowdown is only 1 percentage, right? Okay, so that's it about paging implementation at hardware level. So to brief what we have discussed, in the sense, the simplest way to implement paging is to use CPU registers. But CPU registers can be used for paging if it is if the size of the page table is small. Otherwise, it cannot be used. If the size of the page table is large, then we should go for a technique which is called as PTB, or page table based register, and page table limit register. Okay, so but the drawback with the PTBR technique is there are two memory access, two times the memory should be accessed, and which is so the memory access is slowed by a factor of 2. So this delay is intolerable under many circumstances, considering the what you call considering the importance of CPU utilization. So we are going for the next technique, which is called as TLB, translation look aside buffer, which is a special small fast lookup hardware cache. And we have discussed how TLB works, what is TLB hit, what is TLB miss, and also we have discussed what is ASID, address space identifiers. Fine, let us stop here. Thank you.